Good morning. Today we are going to start the chapter NMR spectroscopy. Introduction. During the last 60 years or so, the use of spectroscopic method has completely revolutionized the approach to structural problems and research in the field of chemistry. The student has already studied ultraviolet and infrared spectroscopy in detail in the previous class. We would now take up the study of nuclear magnetic resonance (NMR) spectroscopy, which was introduced by Felix Bloch and Edward Purcell in 1946 and is easily the most powerful tool for structure elucidation and identification of organic substances. Nuclear magnetic resonance spectroscopy is now divided into proton magnetic resonance spectroscopy (PMR) or 1H NMR and 13C nuclear magnetic resonance spectroscopy. Carbon nuclear magnetic resonance spectroscopy was introduced only around 1970. We would, however, consider here only proton magnetic resonance spectroscopy in detail, starting with the basic principle involved in NMR spectroscopy. Principle of NMR spectroscopy. Like electrons, the nuclear particles, that is, proton and neutrons, are also considered to spin around their axis. If the particle in a particular nucleus do not have their spin paired, the nucleus as a whole will have a resultant spin designated as 1. Now, an atomic nucleus is associated with electric charge and therefore, like any other spinning charge, the spinning nucleus gives rise to a magnetic moment along the axis of spin. Therefore, such a nucleus acts like a tiny bar magnet. It is the presence of these magnetic nuclei in most of the molecules which forms the basis of NMR spectroscopy. Nuclei having resultant nuclear spin. The resultant nuclear spin of an atom is related to the number of protons and neutrons present in the nucleus. Or in other words, it depends upon the mass number and atomic number of the element. In order to have a resultant spin as a whole, the nucleus must have either odd mass number or odd atomic number. The nuclei having even mass number and even atomic number have zero resultant spin and do not exhibit magnetic properties. For example, C612, oxygen, sulfur have nuclear spin 0. It may be pointed out that for nuclei having a net spin as a whole, the numerical value of nuclear spin quantum number depends upon the number of protons and neutrons having parallel and anti-parallel spin. PMR spectroscopy. The simplest nucleus having magnetic properties is the hydrogen nucleus, consisting of a single proton, and we shall be concerned with the NMR spectra of only those molecules which contain proton as a nuclei with magnetic properties. The field of spectroscopy dealing with the NMR spectra of only hydrogen nuclei or proton is often referred to as proton magnetic resonance spectroscopy. But the basic principle of NMR spectroscopy are also same, irrespective of the nature of magnetic nucleus concerned in a particular case. The nuclear spins of the proton of a given sample are normally oriented randomly, but when a compound containing hydrogen and therefore proton is placed in an external magnetic field, the protons may adopt one of those two possible orientations with respect to the external magnetic field. Either the proton can orient so that its magnetic moment is aligned with the applied field, or it may orient so that its magnetic moment is again aligned against the applied field. By convention, protons with spin state plus half are said to be aligned with the applied field, while the protons with spin state negative half are said to be aligned against the magnetic field. Of the two states of orientation, orientation with the applied field is lower in energy or more stable than the orientation against the applied field. The difference in energy between the two stable states is designated as del E. In general, the value of del E is very small, but its magnitude varies directly with the applied field strength. It is evident that the exact amount of radio frequency energy required for the flipping of the proton spin state will depend upon the strength of external magnetic field. The fundamental relationships between the magnitude of del E, frequency of radiation absorbed, and the strength of the applied magnetic field are shown below. Del E is equals to gamma h naught upon 2 pi, where h is Planck's constant, gamma is a nuclear constant and known as gyromagnetic ratio. It is the ratio of angular momentum of atomic systems to its magnetic momentum. It has a different values for different nuclei. For a proton, value of gamma is equals to 26750. It's obvious that the higher the applied magnetic field strength, the higher the frequency of the radiation required to flip the proton to less stable state. Precessional frequency of a proton. It may be defined as equal to the frequency of electromagnetic radiation required to induce a transition from one nuclear spin state to another. PMR spectrum. Origin of signals. In principle, a PMR spectrum could be obtained by placing the substance containing hydrogen nuclei or proton in a magnetic field of constant strength and passing a radiation of varying frequency through the substance. At a certain frequency of radiation, energy of the radiation would match the energy required to flip the proton. This radiation would be absorbed by the proton and frequency could be recorded. In actual practice, NMR spectrometers usually operates by keeping the applied radio frequency constant and varying the strength of applied magnetic field. At some value of field strength, the energy of radiation is just sufficient to flip over the proton and absorption of the radiation take place. This gives rise to an absorption band commonly called a signal. PMR spectra are recorded on charts which show the applied field strength from left to right. Left of the chart is called low field or down field, while right side is called high field or up field. If all the protons in a molecule were to absorb the radiation at exactly the same applied magnetic field strength, the PMR spectrometer would consist of a single signal and a PMR spectroscopy would have very little utility. Fortunately, however, it is not so in the actual practice. This is because the field strength at which absorption by a particular proton take place is strongly influenced by local environment of the proton, such as electron density around it and the presence of other protons as in its neighborhood. As a result, the magnetic field strength which a proton actually experiences is not the same as the applied field strength. Rather, it is the applied field strength modified by the local environments of the proton. A proton having different environments than another will require somewhat different applied field strength to experience the same effective field strength at which absorption take place. It follows, therefore, that at a given radio frequency, the proton having different environments absorb at the same effective field strength, but they absorb at different applied field strengths. Since the absorption is plotted against the applied field strength, PMR spectrum consists of many signals which give very useful information about molecular structure. NMR spectrometer. A simplified diagram of an NMR spectrometer usually employed known as sweep or continuous wave spectrometer is given below. The spectrometer consists of four parts. A powerful magnet whose magnetic field can be varied. a radio frequency generator which emits a precise frequency, a detector which monitors the absorption of frequency and amplifies the electronic signals, a recorder, chart, paper calibrated in frequency units on which the signal is displayed. Now, positions of signals and chemical shift. We have learnt about that the number of signals in a PMR spectrum tells us about the number of types of protons that a molecule has. At the same time, the position of the signals reveals the actual nature of protons, that is, whether the protons are aliphatic, aromatic, vinylic, acetylenic, or hydroxyl, etc. Shielding and deshielding of proton. For determining its PMR spectrum, a molecule is placed in a magnetic field. This causes the electrons of the molecule to circulate, and in doing so they generate secondary magnetic fields called induced magnetic fields. The induced magnetic field may either oppose or reinforce the applied field. For example, circulation of electrons about a given proton itself generate a magnetic field which opposes the applied field. On the other hand, circulation of electrons, particularly the pi electrons about the neighboring nuclei, generates a field which may either oppose or reinforce the applied field. If the induced field opposes the applied field, the effective field strength experienced by the proton decreases. This is called shielding of the proton. Compared to a naked proton, a shielded proton requires a stronger magnetic field to produce an absorption signal, or in other words, it absorbs a field. If the induced field reinforces the applied field, the effective field strength experienced by the proton increases. This is called deshielding of the proton. A deshielded proton naturally requires only a smaller applied field to give a signal, that is, its absorbed downfield. Whether the induced field opposes or reinforces the applied field depends upon the manner in which pi electrons circulate under the influence of applied field. For example, when a benzene derivative is placed in a magnetic field, the delocalized pi electrons of benzene ring are induced to circulate in such a way that induced magnetic field reinforces the applied field at the aromatic protons. As a result, aromatic protons experiences a greater magnetic field strength, or in other words, they get deshielded. Now moving to our next section, chemical shift and their measurement. As explained above, the proton in different environment in a molecule would give absorption signals at a different field strengths due to the difference in extent of shielding or deshielding experienced by them. In order to identify the chemical environment of different kind of protons in a sample, the phenomena of shielding and deshielding have been put on a quantitative basis. For this purpose, the field strength at which different kinds of proton give their respective signals are recorded with reference to a standard signal. The standard or a reference chosen is a sharp signal from tetramethylsilane TMS. TMS give a sharp signal in a position quite removed from the signals of the most other proton in organic molecules. A small quantity of TMS is added to the sample under examination while recording its PMR spectrum. The shift of the position of PMR signals of different proton in a given sample relative to the signal of TMS are referred to as chemical shifts. Reason for taking TMS as a reference compound. First, TMS has 12 equivalent protons and give an intense single signal. Second, the electronegativity of silicon is very low as compared to carbon. As a result of this, the shielding of equivalent proton in TMS is more than that of almost all the organic compounds. Consequently, with reference to TMS signal, Almost all other signals appear in the downfield direction. TMS is chemically very inert and has a very low boiling point, so that it can be easily removed by evaporation after the spectrum has been recorded. In this way, the sample of the compound under study can easily be recovered. Now, factors influencing chemical shifts. The main factors which influence the chemical shifts are inductive effect, anisotropic effect, hydrogen bonding. Inductive effect. Electronegative atoms such as halogen, oxygen and nitrogen deshield the proton and therefore absorption takes place downfield. For example, the proton in dimethyl ether show a signal more downfield than the proton of ethane. The extent of deshielding is directly proportional to the electronegativity of halogens, oxygen or nitrogen's atoms and its nearness to the proton. For example, the protons in CH3F are deshielded to greater than the protons in CH3Cl. Similarly, protons in CH3CH2Cl, there is a greater deshielding of proton labeled A than the proton labeled B. To sum up, an electron withdrawing group reduces electron density around the proton and deshields the proton. On the other hand, an electron releasing group increases the electron density around the proton and results in the shielding. Anisotropic effect. Space effect. Anisotropic effect constitute shielding and deshielding effects on the proton due to induced magnetic fields in other parts of the molecule which operates through space. For example, when a magnetic field is applied to a molecule containing pi electrons, these electrons begin to circulate at right angles to the direction of the applied field, thereby producing induced magnetic field. The effect of this field on the nearby protons depends upon the orientation of the protons, which represent to the pi bonding producing the induced field. For instance, anisotropy accounts for the strong deshielding of aldehydic and aromatic protons. On the other hand, the circulation of electrons of pi system has a shielding effect on acetylenic protons. Hydrogen bonding. If a hydrogen atom is involved in hydrogen bonding in a compound, it will get deshielded due to the strongly electronegative atom attached to it. As a result, such absorption is shifted downfield. Important generalizations. Based upon above discussion, a few important generalizations about molecular structure and chemical shifts are given below. First, if local environments are otherwise equivalent, the more the number of hydrogen on a carbon, the greater is the shielding and more of filled is the absorption signal. Second, electronegativity atoms such as halogens, oxygen, nitrogens deshield the proton and the absorption takes place downfield. Third, the pi electrons of an aromatic ring have strong deshielding effect on the attached proton. Fourth, the carbonyl group deshields a proton on adjacent carbon. Fifth, hydrogen bonding deshields the proton concerned. Sixth, strongly electropositive atoms such as silicon increase the electron density near the proton and in this way they shield the proton. The absorption naturally takes place upfield in such cases. Now, peak area and proton counting. We have already seen the number of signals in PMR spectrum of a given sample gives us information about how many kinds of equivalent protons are present and the position of signals are related to their environments. It is also possible to estimate the number of protons giving rise to a particular signal by measuring the relative intensities of the signal. The intensity of the peak means the area under which the peak and under the peak and not merely the height of the peak. The area under a particular peak is directly proportional to the number of equivalent protons, which gives rise to the signal. The relative areas under the different peaks would thus reveal the relative number of protons of different kinds present in a molecule to the given sample. The peak areas of different signals are measured by an automatic integrator and are generally shown on the spectrum in the form of stepped up curves called integral curves. Height of the integral curves are proportional to peak areas. The relative ratio of peak areas is then converted into a simple whole number ratio. This ratio or simple multiple of it gives the number of protons of each kind. For example, in PMR spectrum of toluene, the steps heights of the respective signal due to methyl and aromatic rings protons are in ratio 3 is to 5. This naturally represents the simplest whole number ratio of the two categories of the proton. Now, since the molecular formula of the toluene is 2bC7H8, the actual number of methyl and aromatic proton must be 3 and 5 respectively. Now, splitting of signals, spin-spin coupling. We have stated earlier that the number of signals in a PMR system is equal to the number of type of protons present in the given molecule, there being only one signal for each every set of equivalent proton. This is no doubt found to be so in some cases, but the actual PMR spectra of the most of the compound are found to be much more complicated than expected on the basis of above statement. Let us, for example, consider the molecule of 1,1,2-tribromomethane, ethane. It contains only two types of proton and therefore its PMR spectrum may be expected to have two absorption peak, but in actual practice its PMR spectrum shows as many as 5 peaks. So, the cause of splitting. The splitting of a signal is determined by the environment of the absorbing proton with respect to neighboring protons. Due to the different spin states and the resultant magnetic moments of the neighboring protons, the actual magnetic field experienced by the given protons may be modified in number of ways. As such, the absorbing proton may experience each of the modified fields and its absorption signal may split into different peaks. Thus, it is the spin-spin coupling of the absorbing and neighboring protons which is responsible for splitting of peaks. To further illustrate this point, let us consider a case of adjacent carbon atoms carrying two secondary protons and one tertiary proton respectively. The effective magnetic field experienced by a secondary proton at a particular moment is naturally modified by the spin of the neighboring tertiary proton. The effective field is increased if the spin of the tertiary proton happens to be aligned with the applied field at the moment, while its effective field decreases if the tertiary proton happens to be aligned against the applied field. Now it is reasonable to assume that at any given moment the probability of alignment of tertiary proton with the applied field would be same as that against the applied field. In other words, we may say that half the molecules the secondary protons will feel an increased effective field and absorption will take place slightly downfield. On the other hand, for the other half of the molecules, the secondary protons will experience a decreased effective field and absorption will shift it upfield. Thus, the absorption signal is split into two peaks called a doublet with equal intensities. Now we will see rules for splitting of protons signals. Spin-spin splitting is a reciprocal process. This means that if one proton splits the signal of another proton, another proton must split the signal of first. The following set of rules may be found very helpful in predicting the interpreting the signal of proton signals. Splitting of a proton signal is caused mainly by neighboring or vicinal protons, which are not equivalent to the proton under consideration. Non-equivalent protons are, of course, those protons which have different chemical shifts. For instance, in the spectrum of CH2Cl, there is no splitting as the vicinal protons are equivalent to one another. Second, splitting of one proton by another on the same carbon is very rarely come across because such protons are generally equivalent to each other. But if the protons on the same carbon are non-equivalent, they will split each other. Third, the mutual splitting of protons separated by more than two atoms, known as long-range coupling, is also very uncommon. N plus 1 rule. The number of peaks n into which a proton signal is split is equals to 1 more than the number of proton small n which causes the splitting, that is n capital N is equals to small n plus 1. Now, coupling constants. The distance between the peaks in a given multiplet is known as coupling constant. Coupling constant are denoted by the symbol J, and coupling constant between two protons marked A and B is represented by JAB. The value of coupling constant is expressed in Hertz, and it is a quantitative measure of the magnitude of splitting effect. Unlike chemical shift, the value of J depends only on internal forces and is independent of applied field strength. Therefore, coupling constant measure on an NMR instrument operating at 60 mH will be the same as those measured on the instrument operating at 300 mH or any other field strength. Magnitude of coupling constant. The value of coupling constant is determined by the number and the kind of intervening chemical bonds and spatial relations between the proton are illustrated below for a few cases. First, for non-equivalent protons attached to the same carbon atom, that is geminal protons, the value of J varies from 0 to 20 Hz depending upon the bond angle and overall structure of molecule. Second, the proton attached to adjacent carbon atom, vicinal protons, J varies from 2 to 18 Hz depending upon the spatial position of proton and structure of molecule as whole. 2 subpart 1. In case of freely rotating groups, for example protons with anti-conformations, J is equals to 5 to 12 Hz, while protons with gauche conformation, J is equals to 2 to 4 Hz. In case of vicinalic protons, when restricted rotation due to double bond is involved, the cis proton have J is equals to 6 to 14 Hz, whereas trans proton have J is equals to 11 to 18 Hz. In case of allylic protons, J is equals to 2 to 13 Hz. In case of aromatic protons, in ortho position, J is equals to 8 to 11 Hz. Coupling constant are measure of effectiveness of spin-spin coupling and have been very useful in getting exact information from PMR spectra of complex molecular structures. Now moving toward the applications of PMR spectroscopy. PMR spectroscopy provides the most informative tool in the study of organic chemistry. Some of its important applications are presented below. First, identification of substances. Like infrared spectrum, the PMR spectrum of a substance also serves as a fingerprint of the substance. If the PMR spectrum of a given sample is exactly the same as that of a known substance, the given substance must be identical with the known substance. In this way, PMR helps in establishing the identities of substances. Second, Determination of molecular structure. A prominent feature of PMR spectra of most of the substances is their high complex nature. This complexity is no doubt helpful because it makes the spectra very characteristic and better suited as a structural tool, but at the same time, it renders the interpretation of spectra a very tough and highly specialized job. Fortunately, with the help of isotopic substitution and techniques such as double resonance, it is now possible to analyze completely even the most complex PMR spectra. Therefore, the PMR spectroscopy is being increasingly used as the most powerful tool for structure elucidation. Distinction between geometrical isomers. Due to the difference in the chemical shift as well as coupling constant, the cis and trans isomers of compound can easily distinguished from each other. Fourth, detection of hydrogen bonding. If a hydrogen atom is involved in hydrogen bonding, it will get deshielded due to the strongly electronegative atom attached to it. As such, absorption is shifted downfield. The extent of intermolecular hydrogen bonding varies with the nature of solvent, concentration of solution, and the temperature. For example, is concentrated solution hydroxyl protons absorb around 4 to 5 del, while in a dilute solution the absorption takes place at higher field around 1 del. It is also useful to note that intramolecular hydrogen bonding also shifts the absorption downfield, but the shift does not depend upon concentration. This observation can be used for distinction between now determination of relative amounts of tautomers. PMR spectroscopy is also being used to determine the relative amounts of tautomers in a tautomeric mixture. Let us consider the example of acetyl acetone, which exists as an equilibrium mixture of enol form. The PMR spectrum of acetone shows following signals for equivalent protons. There is a distinct 2 proton signals at del 3.6 due to CH2 proton of keto form, while there is a signal at del 5.5 due to double bond CH proton of enolic form, but the intensity of the 1 proton signal of enolic form is 2 times the intensity of 2 proton signal of ketonic form. This can be possible only if the equilibrium mixture contains more molecules of enolic form than the ketonic form. The ratio of the two types of molecule can be determined as follows: number of protons per molecule in keto form upon number of protons per molecule in enol form into number of keto molecules upon number of enol molecules equals to intensity of CH2 signal upon intensity of double bond CH signals. Identification of reaction products. Since the PMR spectrum helps to establish the presence or absence of various functional groups and other structural features in different substances, it can be used to identify the products of practically every reaction carried out in the laboratory. For example, in addition reaction of HCl to 1-methyl cyclohexane, formation of two products is possible. PMR spectrum of the reaction product exhibit a single unsplit peak for the methyl protons. This shows that the product form is 1-chloro-1-methyl cyclohexane expected from Markovnich's rule. Now, interpretation of PMR spectra. PMR spectrum of a substance gives very valuable information about its molecular structure. This information is gathered as follows. First, number of signals. The number of signals in PMR spectrum tells us how many kinds of proton in different chemical environment are present in the structure under examination. Chemical shifts, position of signals. The position of signals tell us about the electronic environment of each kind of proton. Area under each peak. The electronically integrated area under each peak tell us about the relative number of protons of different kinds. Fourth, splitting of signals. Splitting of signals tell us about the environments of absorbing proton with respect to environments of neighboring protons. Note, in the case of signals where splitting take place, the position of signal is judged from the center of doublet or triplet, etc. Useful generalization about the position of signals. The chemical shifts of or position of the signal due to different kinds of proton are given in but the following generalization about the environments of a proton and the position of its absorption signal can be quite useful in the interpretation of spectra. First, proton on a saturated carbon not attached to heteroatom or unsaturated carbon atom absorb in the region of del zero point 0.9 to 1.5. Proton in a saturated carbon which is attached to a heteroatom or an unsaturated carbon atom as shown below absorbs in the region del 1.5 to 4.5. Acetylenic protons absorbs at del 2 to 3. Vinylic protons absorb at del 4.6 to 5.6. Aromatic protons absorbs at del 6 to 8.5. Alcohol hydroxyl protons absorb at 1 to 5.5. Aldehyde protons absorb at del 9 to 10. Carboxylic protons absorb at del 10.5 to 12. It must, however, be emphasized that interpretation of PMR spectra of most of the compound is not a very simple task, but the fundamental principle learned here do help us in making the beginning in this direction. Now moving to our limitations of PMR spectroscopy. Even though PMR spectroscopy has proved extremely useful in the study of chemistry and has opened up new areas of research and discovery, it has certain limitations as given below. First, the PMR spectra of organic compounds are quite often very complicated and difficult to interpret. Second, for recording the PMR spectra, only liquid samples are usually employed. The liquid solution may be the solution of the compound in a suitable solvent, or if a compound is a non-viscous liquid itself, the neat liquid can be used. Third, a serious limitations of PMR spectroscopy is its low sensitivity. The minimum sample size is 1 ml with a minimum concentration of about 1%. PMR spectroscopy indicates only the relative number of protons and does not provide any information about molecular mass. It must be said, however, that with improved instrumentation problem of low sensitivity has been overcome. At the same time, new techniques such as double resonance and deuterium labeling are providing very helpful in the simplification of PMR spectroscopy and analysis of complicated spectra. Now we will move towards the last section of our chapter, that is interpretation of PMR spectra of simple compounds. We will take two examples. One is ethanol. The spectrum of ordinary sample of ethanol may be described as follow: triplet, del 1.2, 3 hydrogen of CH3, quaterate, del 3.63, 2 hydrogens of CH2, singlet, del 4.8, 1 hydrogen of OH. Explanation. Ethanol contains three kinds of protons and consequently exhibit three signals as given above. The upfield triplet of del 1.2 is due to the three equivalent methyl protons. Evidently, its splitting into a triplet is due to the two neighboring of the methylene group. The quadrate at del 3.63 is from the two methylene protons. Its multiplicity of 4 peaks is due to the coupling with the 3 methyl protons, there being no coupling with hydroxyl proton. Finally, the downfield signalet at del 4.8 is due to the hydroxyl proton, which does not show any coupling with the adjacent methylene protons. The relative areas under the peak of methyl and hydroxyl protons are in the ratio 3:2:1. An interesting feature of PMR spectrum of an ordinary sample of ethanol is that we may observe any splitting of signal due to coupling between hydroxyl proton and methylene protons, although they are on adjacent atoms. But if we examine the PMR spectrum of a very pure sample of ethanol, it is found that the signal from the hydroxyl proton is split into a triplet and the signal from the methylene proton is split into a multiplet of 5 peaks. This is because in the highly purified sample, the exchange process gets slowed down and the coupling between hydroxyl and methylene proton can be recorded. This slowing down of the exchange process is due to the complete absence of acidic or basic impurities in ethanol, which catalyze the exchange process. Now, moving toward our second sample, that is acetaldehyde CH3CHO. The spectrum of acetaldehyde is as follows. First, a doublet at del 2.2, 3 hydrogen of CH3, and a quadrate at del 9.8, 1 hydrogen of CHO group. Explanation. The doublet at del 2.2 is due to the three equivalent protons of methyl group coupled with a single proton of aldehyde group. The aldehydic proton absorbs far downfield at 9.8. The signals appear in the form of quadrate due to the coupling by 3 protons of neighboring methyl groups. The respective peak areas are in ratio 3:1. This may be summed up as CH3 split into doublet by aldehydic proton and CHO group split into quadrate by these protons of methyl group. Hence, this was our chapter. Thank you.